Dear students, welcome to the lecture number 6 of your mechanical properties of fluids. So, in the last lecture, we have been studying about the Torricelli's law, right? So, we have been studying about fluids since long, and we have been studying about this Torricelli's law, and we studied that, and then we did some applications. I mean, we did, I think, one or two applications. One of them was your venturimeter, right? So there are some other applications as well, such as your dynamic lift, your heart flow, the blood flow in the heart, right? So there are some applications. I will not do all of them. You can study them on your own. It is given very beautifully in your book. Okay. Uh, so today we will study about a different topic which is called viscosity, and this is a very important topic. Okay, viscosity. Now, what do you mean by viscosity? Okay. See, there are some diagrams. It is given very beautifully in your book in figure number 10.14 A and B. Okay, I'll just explain what does these diagrams actually mean. How do you uh, this calculate the effect of this viscosity? See, our fluid. Whenever we have a fluid, okay, this fluid I can divide it into various layers. Okay, layers. That means, say if I have a pipe, okay, if I have a pipe through which my water is flowing, okay, now uh, you might have noticed that uh, if I have any surface, any solid surface, and if I put a drop of water, okay, say for example during the rainy days when the raindrop falls in any solid surface, in your wall or in your bench or wherever, you'll see that that drop of water, it rolls down the surface, but when it rolls down, I mean there is some water left out during its path, right? If my water falls down from top to bottom by rolling down in any surface, say in a wall, if the raindrop falls on the wall, okay, the raindrop will start falling down. So during its course of falling down, you'll see that there is some water which is left behind. Okay, now why is it left behind? Because there is some force. Okay, there is some force between this raindrop and the wall, between this solid and the liquid. Okay, you can say that it is a kind of an adhesive force, not exactly, but it is a kind of this adhesive force, because of which the water, when it falls down, right, I mean it gets stick to the surface. Okay, and because as it gets stick on the surface, the velocity initially is higher, but later on the velocity of the raindrop, when it falls down through this surface, by rolling down through its surface, it decreases. Okay, uh, so it can also be understood like this. Say if you have a pipe in which my water is flowing, okay, so if my water is flowing through a pipe, uh, if I have this pipe like this and my water is flowing, so see, just at the boundary of the pipe, okay, just uh, I mean the edge of the it is not edge, but the boundary or the wall of the walls of the pipe, right, the two sides, right, the two edges of this pipe or the wall of the pipe, the liquid is sticked, right? I mean, when it flows, it is in direct contact with the wall. But as we move from the corners, okay, I mean from the sides of the pipe to the center of the flow, I mean the center at which the liquid is flowing will have less restriction, right? The restriction to the flow of the liquid will be very high towards the two sides of the pipe, but towards the middle, the restriction will be very less. Why? Because this the liquid is now at the middle. It not is not just adjacent to the sides of the wall. Okay, the liquid is just flowing to the center, but in the sides of this pipe, uh, the liquid is adhere to the surface of the pipe, right? That's why it will face some restriction. So accordingly, what will happen, more you come towards the center of this liquid flow, the velocity of the liquid is highest. Okay, but along the sides of this pipe the velocity of the liquid is less. That's why, see here I have drawn some velocity vectors. Okay, and the velocity vectors at the center, it has a high velocity. That's why the length of the vector is long, which I have drawn here. You see that the length of the vector is long at the center of the liquid flow. And the two sides, the vector I have drawn small. Why? Because of the restriction, the velocity will be less. But the center, just at the middle portion, the velocity will be highest. So this restrictive force which the fluid experiences when it comes in contact with any other solid body or so, that restrictive force is called this viscous force. Okay, and this phenomena is called viscosity. Okay, I have not written all the details here as it is given in your book. You can, if you can read the book and you can understand, okay, the definition it is given there. So this restrictive force which the fluid is experiencing, that is called this viscous force, and this phenomena is called viscosity. Okay, so what will happen is the liquid which is just stick to the surface, that will experience a very high force, and which is apart from this surface, that will experience a low force. So this liquid which is flowing just at the surface, because this is the bottom, right? The liquid is the fluid is stick to this bottom. So here this part is sticked, but so the force is very strong, so this will not move. This can be considered that it is stick to this boundary, but as we move away from this boundary, at this point the force is less, so the liquid will move. So the shape of the liquid is not changed. Earlier the liquid shape was A, B, C, D. Now it is A, E, F, T. Okay, so there is a bit of displacement. It looks like that there is a kind of strain which is the liquid is experiencing because of this motion, right? Now if there is a strain, then of course there is a displacement from this position, right? At the bottom it is fixed, no problem, but in the upward, in this away from this edges, the sides, it is experiencing a kind of strain. Okay, and there is a kind of displacement. So let this displacement be delta x. Okay, and delta x will be what? Velocity into time. So in that time interval delta t, the displacement x is given by delta x is equal to v into delta t, where v is the velocity of the fluid. Okay, so this is a displacement. This part b to e, this is a displacement. I have written b here, it should be written here. Okay, exactly that position. They refer to diagram 10.14. Okay, so b to e, this is the displacement delta x. Delta x is equal to v del t. So the liquid at ABCD shape take the shape of AEFD after short interval of time delta t, right? During this time interval, the liquid has undergone a shear strain of delta x by L. Okay, delta x by L. So delta x by the length, whatever length my liquid is originally extended, that is the length L, and delta x is the displacement which is caused, right, because of this force. So delta x by L is the strain. Okay, now unlike a solid, okay, the stress depends on the rate of change of strain or strain rate. Okay, because see, in case of a solid, which we have already studied in the last lecture in mechanical properties of solids, what we have studied is that the stress is directly proportional to strain. But in case of liquid, the stress is directly proportional to the rate of change of strain. That you have to remember. Okay, in case of a solid, the stress was directly proportional to strain, but in case of a liquid, the stress is directly proportional to the rate of change of strain. So the rate of change of strain will be nothing but if you divide this entire quantity by delta t. So delta x by L is there, and you divide by delta t. So that is the rate of change of strain. This is the strain, and the rate of change of strain will be just this whole thing divided by delta t. Okay, Now delta x by delta t is nothing but v, velocity, right? And this is the length L. So v by L, okay, v by L. So stress is directly proportional to v by L. Now the coefficient of viscosity eta, the coefficient of viscosity eta, okay, so this is eta. I have written it like this. This is a symbol, Greek symbol eta, and this is called the coefficient of viscosity because my liquid is now experiencing a viscous force. So there is a coefficient of viscosity through which we can measure how viscous the liquid is. Okay, so more is this value, more resistance it will offer. Okay, so the coefficient of viscosity eta for the fluid is defined as the ratio of shearing stress to the strain rate. Okay, the ratio of shearing stress, the ratio of shearing stress to the strain rate. So eta is equal to stress F by A, force per unit area, divided by strain rate V by L, which we have just obtained here, V by L strain rate. And stress is nothing but your force per unit area. So eta is equal to ratio of stress by strain rate. So L will go up, A will come down. So FL divided by VA. So this is the definition for your coefficient of viscosity. Okay, this is the definition of your coefficient of viscosity, right? Now if I want to calculate the what I say, the unit of viscosity, what could be the unit? See, F by A, force per area, is nothing but your stress, which is Newton per meter square, right? And again L divided by V is, it is meter and it is meter per second, so ultimately you will get second here in the numerator, so it will be Newton per meter square second. Okay, Newton second per meter square, same thing. So Newton per meter square is nothing but Pascal, and this is S. So the unit, the SI unit of viscosity is given as Newton per meter square second. It is Pascal second. Okay, fine. So this is what viscosity is all about. Okay, and we have to remember this expression of coefficient of viscosity. Remember that it is directly, the stress is proportional to the strain rate and not strain. Okay, this is unlike solids. Okay, fine. So we have obtained this formula. Now there is an example 10.9 in your book. You just refer to the example. I have not written the question here. The problem I itself have not written, but the solution I have done, and it is already solved in your book. So it is a worked out example. So it is given that there is a ball of mass, this much mass is given, your length is given, area is given, okay, and I can easily calculate the strain rate, right? This is V by L. So V is also given, so that is your 0.085 is the velocity with which the liquid is flowing, right? L, it is already given, initially it is 0.30 millimeter, and you have to convert this into SI units. So 0.3 into 10 to the power minus 3 meter. Okay, so this is your SI unit, and this is the case. So eta is equal to what? It will be stress divided by strain rate, right? So strain rate we have already obtained, and stress is nothing but force per unit area, and force is, it is given that 9.8 into 10 to the power minus 2 Newton, and by area it is given 0.10 meter square. So force, and this is area, and now I will have L and V. So L in the numerator, it is 0.3 into 10 to the power minus 3 meter, and V is nothing but your 0.085 meter per second, right? So now you just do the calculation and you will get some value. This is the value for the coefficient of viscosity, right? And I have just used this formula here and nothing else is done. Just you put the formula for force, length, velocity and area, you will get this. This is a very simple example. Okay, coefficient of viscosity. Okay, now since we have studied about this coefficient of viscosity, there is another law which depends upon this coefficient of viscosity, that is called the Stokes law. Okay, this is called the Stokes law. Now when a body uh, say if I have say if I throw a ball in a pond or a river, okay, so if I do it that way, then what will happen? The ball will fall. I mean, the ball will start going deep inside into this river, right? And as this ball starts moving deep down and down, what will happen? Will the velocity at which the body was, I mean the ball was initially going into the water, will remain same with the depth of the water? No, the velocity will decrease, right? First, when the ball falls into the pond, it will move with some velocity, and finally the velocity will start decreasing. Why does that happen? Why does my velocity decrease? Because the water is putting some force on the ball. Okay, the ball is experiencing some restriction. Okay, because the layers of the fluid or water, whatever you say, so those are causing some restriction in the flow, in the motion of the ball. Okay, and that restriction, as I already mentioned, that there is a kind of retarding force. Okay, there is a force which restricts, so the velocity it decreases, and this retarding force which a body is experiencing, that depends on the viscosity eta of the fluid. Okay, that means when uh, this solid body it falls to the fluid, then this fluid it gets sticked to the solid surface, right? And why does it get sticked? Because of this viscous nature, correct? And because of that, it will go on experiencing a retarding force. It will experience some restriction in the in its motion through this fluid. That's why the velocity will decrease. Okay, and the end the velocity will not be the same as it was in the earlier, right? And this kind of restrictive force is actually everywhere. If you throw a ball through air, okay, anything, if you throw through air, right, then also because of the force experienced by this ball due to air, the air will also offer some restrictive force, right? So air is also a fluid actually. So there is also a coefficient of viscosity for air as well. But for fluid, the more the density of the medium, the more will be the coefficient of viscosity. So we'll not go much into the details of that. So because of this viscous nature only, it experiences a restrictive force, or you can say that it experiences a retarding force, which decreases its velocity, the velocity of the solid body through this fluid or air. Okay, so Sir George G. Stokes, so he's the, so this is the name of the scientist which gave this law. Okay, an English scientist gave the viscous drag force. Okay, viscous drag force F as 6 pi eta a v. A is the radius of the body, eta is the coefficient of the viscosity, v is the velocity with which the body is initially flowing. Okay, 6 pi eta a v, and we will not go to the derivation of this. The derivation we do not need to do here at present. Okay, so this is known as Stokes law. You just remember this law. Okay, this is known as Stokes law. Now if I take a raindrop, okay, in case of a raindrop in the form of a sphere, as it moves, I mean as it falls down from the sky, right? So my raindrop, it is actually flowing through air. I mean it is falling down and it is coming through air, right? So it will also experience a restrictive force, a retarding motion, right? So there will also be some frictional force, right? Because see, why does this restrictive force come? Because there is a frictional force between the different layers of this liquid and the solid, right? Because of this frictional force only this retarding force is coming. So when it is coming through, it is falling through air, then what is happened, that it is coming with a constant velocity. So there will be an equilibrium, right, where the uh, buoyancy force and this viscosity plus viscosity force will be equal to the gravitational force, and this terminal velocity Vt is given by this one. This is just a formula which is given 6 pi eta a Vt. So this is given, the derivation will not do here. So finally Vt is a terminal velocity. Okay, I mean the end, at the end when this force is exactly balanced by the force due to gravity, because gravitational force is in the downward direction, and the force explained by the raindrop will be in the upward direction because this viscous force and whatever, right? So this will be balanced each other, and then finally there will be terminal velocity which is given by this expression. Okay, so rho and sigma, these two things are two, this is the mass density and this is the density of your fluid. Okay, so rho is the mass density of the ball or raindrop, whatever, and so this will be your fluid. G is the acceleration due to gravity, L with the radius, eta is the coefficient of viscosity. Okay, so you are finally getting the value of this terminal velocity. So this is the velocity which the ball or anything will ultimately reach. Okay, so this has come because of this viscosity. Okay, just remember that so today we'll stop up to this point. Okay, so today we have studied about viscosity and a law which depends upon viscosity, that is called the Stokes law. So just remember that so there are different layers of fluid which are experiencing some force with each other because of the friction. Okay, the actual reason is the friction, because of which there is experiencing some retarding force, and because of that I'm getting a force. There's some force is called the viscous force, and the phenomenon is called the viscosity. Okay, and then depending upon that we have the Stokes law. Okay, so this much is for today, and next day we'll continue from this point, and you have to go through this example. Okay, example 10.10, and I have not written all the details of, for example, viscosity and Stokes law here, so you just go through the book and the definitions are given them in a proper manner, and go through this example 10.10. There this formula is used. Okay, in example 10.10 in your book, using this formula the terminal velocity is obtained. Okay, so go through this example. So this much is for today. Thank you.